Okay, let's dive right into this. You know, when most of us think about pest control, we probably picture just a simple can of bug spray, maybe a quick squirt in the corner of a room, and that's it. But the reality of modern pest management, it is actually a highly sophisticated, completely unseen science operating right under our noses. Welcome to this explainer. Today we're going to decode the incredibly precise, deeply biological, and constantly evolving world of pest management. We'll be breaking down the exact tools, the chemistries, and the biological strategies used to keep our environment safe and healthy.
Here's the roadmap for our explainer today. We're going on a macro to micro journey, starting with the technician's toolkit, then moving to precision and application, formulations as delivery vehicles, chemical classes and payloads, disrupting the infect, and finally, the arms race of resistance. So let's start with section 1, the technician's toolkit. Pest control is so much more than just holding a spray can. Now, what's really interesting here is that before a single drop of product is ever applied, a lot of highly structured groundwork has to happen. The physical reality of a technician's day-to-day work actually looks way more like a home inspector's kit than an exterminator's. You've got sturdy flashlights, drills, clipboards for documentation. These are literally the tools of a diagnostic investigator. The goal isn't just to go in and spray, it's to investigate, to monitor, and to really understand the structural environment before deciding on any course of action. And that investigative mindset brings us to these unexpected essentials. A really well-outfitted technician relies on things like mirrors to see behind and under heavy equipment. They use moisture meters because, well, water is often the primary driver of an infestation. They deploy flushing agents to force insects out of hiding, magnifiers for precise biological identification, and digital cameras to document the exact conditions they find. It's a diagnostic science, through and through. Which leads us to section 2, precision and application. How are these physical tools actually used in a space? Once the environment is properly diagnosed, the next step is applying the right solution in exactly the right way. Application methods are strictly categorized, and two of the most foundational concepts are broadcast and barrier applications. A broadcast application is designed for broad expanses. Think of treating entire floors, walls, ceilings, or large outside areas. On the flip side, a barrier application is highly localized. It targets specific thresholds, perimeters, and entry points with the sole intent of just keeping pests out of a designated area. But often, even more precision is required. Enter the crack and crevice application. Technicians use this incredibly precise technique to apply tiny amounts of material directly into inaccessible voids, cracks, and structural crevices. The beauty of this method is that it places the control measure exactly where the pests actually harbor, while practically eliminating the risk of humans ever coming into contact with the material. It's totally targeted. Okay, moving on to section 3, formulations, or what I like to call delivery vehicles. Let's zoom in a bit. Now that we've seen how it's physically applied to a wall or a crevice, let's look at what's actually inside the sprayer. Think of these as the delivery vehicles for the active chemistry. Two super common ones are emulsifiable concentrates, or ECs, and wettable powders, or WPs, and they each have distinct trade-offs. ECs mix easily and leave little to no visible residue on a surface. But because they're oil-based, they're easily absorbed through skin or into porous surfaces like unpainted wood, making them far less effective there. Wettable powders are the opposite. The active ingredient is mixed with a solid dust. This means way less skin absorption, and they sit nicely right on top of porous surfaces. The catch? They often leave a highly visible powdery residue behind, and they require constant agitation in the tank so they don't settle to the bottom. Now, one of the more advanced delivery vehicles is microencapsulation, and this is brilliant at the microscopic level. Droplets of the active ingredient are physically encased inside these tiny, slow-release polymer spheres. By carefully controlling the wall thickness and the size of these plastic-like capsules, chemists can create a product that provides improved long-term residual control, has a much lower exposure risk for humans, and is readily picked up by insects as they crawl across a treated surface. Another highly effective formulation is the baits. Baits are incredibly target-specific. They mix a very low percentage of the active ingredient, usually less than 5%, with a food matrix or another highly attractive substance. When placed properly, pests like ants will eagerly feed on the formulation. The main challenge here, though, is that this attractive mixture has to compete with other food sources in the environment. I mean, if a kitchen floor is covered in crumbs, the bait suddenly becomes a lot less appealing, right?
All right, section 4, chemical classes and payloads. Let's talk about what's actually doing the heavy lifting.
So we have the delivery vehicles, but what exactly are they delivering? What is the actual payload? Well, before modern synthetic chemistry, humans relied on nature's own defenses. Historically, botanicals are some of our oldest tools, utilized longer than pretty much anything else than basic sulfur and salt. Think neem seeds or wild chrysanthemums, which give us natural pyrethrum. These plant-derived extracts are fantastic because they usually have a very short residual life in the environment, which generally means minimal impact on non-target beneficial insects. If we map the history of these payloads across the decades, you can clearly see a constant evolution driven by the search for smarter, safer, and more effective solutions. We started with botanicals before the 1940s. The 40s then ushered in the era of highly stable chlorinated hydrocarbons, like DDT. But due to their extreme persistence in the environment, the 60s and 70s saw a shift away from them toward organophosphates and carbamates. Then, by the 80s and 90s, the industry was synthesizing newer classes entirely, like neocotinoids, focusing on highly targeted modes of action. To put that history into perspective, back in 1944, army barracks were routinely sprayed for bedbugs using those chlorinated hydrocarbons. These are basically stable chains of carbon, hydrogen, and chlorine. And while they were highly effective at the time, their environmental persistence just proved to be way too great a cost. That's why most, if not all, of these specific chemicals are completely unavailable in the US today. So as the industry moved away from chlorinated hydrocarbons, they adopted organophosphates and carbamates. Both of these actually act as nervous system toxins by inhibiting an enzyme called choline esterase. The absolutely crucial point here is the safety evolution between these two. You see, organophosphates bind irreversibly with choline esterase, which presents much higher toxicity risks. Carbamates, on the other hand, were developed as a direct safety improvement, specifically because they work via a reversible process of choline esterase inhibition. This gave them a slightly better safety profile for the technician applying them. Moving on to Section 5, Disrupting the Insect. Let's zoom all the way into the biological level. At this molecular level, we can see exactly how modern chemistries stop a pest in its tracks. One of the major breakthroughs was the development of pyrethroids. Instead of messing with cholinesterase like those older chemicals we just talked about, pyrethroids bypass it completely. They act specifically at the sodium pathways in an insect's nervous system. The real beauty of this targeted approach is that mammals are vastly less sensitive to this process, and we can readily metabolize and excrete these compounds. It represented a massive, massive leap forward in mammalian safety. But hey, we don't always have to target the nervous system. Enter insect growth regulators, or IGRs. Instead of acting as a traditional poison, IGRs take a truly fascinating biological route. They essentially sabotage the insect's development and life cycle. Depending on the specific type, they might disrupt the formation of eggs, inhibit the synthesis of chitin so the insect literally can't form a new exoskeleton when it tries to molt, or even mimic juvenile hormones to prevent them from ever transforming into reproducing adults. It's brilliant. No reproduction, no infestation. And that brings us to our final section, Section 6. The arms race of resistance. All of this builds into an ongoing global dynamic. With all this brilliant formulation and targeted biological disruption, we really have to ask ourselves, can pests outsmart our chemistry? And, well, the short answer is yes, absolutely. Pests are living organisms, and they're constantly adapting to the environmental pressures we place on them. This is exactly why organizations like IRAC, the Insecticide Resistance Action Committee, exist today. They publish highly detailed classification systems that group pesticides strictly by their mode of action. Now, why does this matter so much? Because if we continually apply the exact same chemical class with the exact same mode of action over and over again, the few pests that naturally survive will breed, and that quickly creates a population of superpests completely immune to that single chemical class. So rotating these chemistries is absolutely critical. It all boils down to this fundamental reality. All organisms can adapt to pesticides through natural selection. Pest management is not just some static household chore like sweeping the floor. It is a constant, real-time interaction with a highly dynamic biological system. Every single application we make applies an evolutionary pressure that the insect population is actively trying to overcome. And that brings us to the end of our journey today. The unseen science of pest control is truly an ongoing microscopic arms race happening all around us. From the technician's careful diagnostic tools to those tiny polymer-encapsulated payloads targeting specific sodium channels, we are constantly innovating just to stay one step ahead of nature. So I'll leave you with this to consider. As insect populations inevitably continue to adapt, what on earth will the next generation of our unseen scientific solutions look like? Keep that in mind the next time you see a technician at work. Thanks for joining me on this explainer, and as always, keep learning.